Okay, so in this lecture we're going to take a look at calculating numbers based on our Ramberg-Osgood equation and our hysteresis branch and Massing's hypothesis and so forth. So let's have a material that has a K prime of 1800 megapascals, modulus of elasticity of 210,000 megapascals, and an N value of 0.25. We have a time history that I've shown here. It goes up to 500, down to 200, up to plus 200, back down to minus 100, and up to 500 megapascals. The exact time unit for us is not important. We're going to be assuming rate independent plasticity behavior and so forth. Now I've written down the monotonic equation and the cyclic or branch equation. Okay, so the monotonic Ramberg-Osgood equation that we're going to use, sigma over E plus sigma over K prime to the 1 over N prime power. Now I'm assuming that we have a cyclically stabilized material, so I'm going to use the K prime and N prime values. Now for convenience, I'm going to rewrite our branch equation such that I can calculate delta epsilon easily. So I'm just going to take this 2 and I'm going to multiply 2 by both terms to this equation. So I have solve for delta epsilon. So I have a delta sigma over E plus 2 times delta sigma over 2 divided by K prime to the 1 over N prime power. Okay, so this is going to be a little bit more convenient for us. Now, let's see, I need to figure out how to do this in this video. I think what I'm going to try to do is I'm going to add a layer, and I'm going to put our hysteresis branch in this hysteresis plot in this layer. Okay, so I'm going to try to make this big. Now I also need a little bit of room to work, so I'm going to go back to this one, and we'll do our work kind of in this right hand zone right here. In fact, let me do this. Let me get rid of this. And I'm going to put this here. So I have a little bit more room to work. Okay. So we've talked about in the previous lecture how to sketch these things up. So we know what the shape of this should look like. Let's do the calculations. So first of all, I'm going to go from O to A, and from O to A is going to be using my monotonic curve. So I'm going to have the epsilon at point A is going to end up being 500 over, I'll put the numbers in once, but I'll just use the symbols next time, for 210,000 plus 500 over 1800, both of these units are megapascals, to the 1 over 0.25. Okay. So let's see what I got for that, and then I'm going to just check it. So according to my calculations, I got 0.0083335. Now, I would encourage you to get out your calculator and go through these steps yourself. Okay, so that calculation checks out. So let me go back to my stress strain plot. Let's see, I need to be able to edit this. Let me click on that one. And so I don't know the exact shape. We could use a spreadsheet and calculate all the values along this branch if we want. Maybe we'll go back in the end. Maybe I'll go back and do that for us at the end of this video. But for now, we're just going to use the sketch. And we're at a stress level of 500, and we said our strain level was 0.0083335. Okay, so that's the coordinate of that point right there. Now, we go down to B, and it's at a stress level of minus 200. Okay, so we're going to go down to B, and it's a stress level of minus 200. All right, now here's something I don't know yet. And we might adjust this picture in a minute. I don't know if this stress change will cause the strains to go negative or if it will be somewhere in the positive territory. We'll figure that out. We're actually going to calculate that. And if I calculate it and it's not in the negative territory over here, then we're going to erase this line and make some adjustments, and we can make this look a little bit better. But let's do the calculation and see. Let's go ahead and save this again. Right. So now we're going to calculate what goes on the branch from A to B. Okay, so what is my delta sigma that I'm going to use in this equation right here? The delta sigma that I'm going to use is 700. Okay, so it starts up here, goes all the way down to here. So in my delta epsilon then is going to be 700 over E, okay, that's the E value, plus 2 times 700 over 2 divided by K prime to the 1 over N prime power. Okay, let's see what I got for my delta epsilon from A to B. I got 0.0061922. Okay, carried on a few extra digits there, but basically I wanted to have enough so I can do this subtraction. Okay, so what that tells me is that I did not get into the negative territory. If I take the strain at A and subtract this delta epsilon AB, I end up with a small positive value. So let's go back to this picture and clean this up just a little bit. Probably could have had a little better slope to that anyway. Okay, so this is A, this is B. My delta epsilon from A to B was 0.0061922. My strain at position B would be my strain at A minus the delta epsilon. And that tells me that it is equal to 0.002143. Okay, so this point right here is at the stress level. I guess I'm plotting y and x, stress versus strain. And you know, if this was a graph in Excel, you'd go sigma epsilon. But I think you understand what I'm doing here. Minus 200, and then I'd have the point 0.002143. Is that too confusing to have y comma x? Let's go ahead and change it to x comma y. All right. So now we're here at b. Let's think about what happens then for the next excursion. Maybe we'll just make a sketch of what we think is going to happen. So going up to here, we said it comes down to here. It's going to go up to here, and then it's going to here, and then it's going to be closing this one and then closing that one. All right, so the next branch then, so here's A, B, C, D, and then E. The next branch is going to be B to C. Now there's a stress change, a delta sigma from B to C of 400 megapascals. All right, so that's pretty easy. I calculate my change in strain from B to C, 400 over E. It's 2 times 400 over 2 divided by K prime to the 1 over N prime power. And I end up with my delta epsilon of 0.0022096. With this number, I can calculate where my epsilon C is. Epsilon C is going to be the strain at point B minus my delta epsilon BC. For that, I get 0.004352. So let's go back to here. I'm at positive 200. And my strain value is 0.0022096, and then at positive 200. Okay, so far, so good. All right. Now I go from C to D. All right, the delta sigma, we can see from here, but you have to be a little careful with the time history. You'd probably want to use this sketch. We're at positive 200, we go down to minus 100. That's a delta sigma of 300. Now let's go ahead and put the units on there. So we calculate the change, delta epsilon from C to D would be 300 over E plus 2 times 300 over 2 for K prime to 1 over N prime power. And I got my delta epsilon to be equal to 0.001525. which leaves my epsilon d as epsilon c minus delta epsilon cd to be 0.002827. Let's go look at the other plot. Two, 8, 2, 7. So we go from C down to D, and we are just a little bit to the right of point B. We have the point 0.002827, and that is at the stress level of minus 100. All right, let's save this page. Let's save that one. Let's make a little bit of room here. Now this next part is going to be a little, we're going to have to think about it. It can be a little tricky. And the story is in this plot on this page. I'll emphasize it in red. First we go from C to D. Then we go from C to A using the branch equation from B to A. So we're going to look at the loading segment D to E. Gets us back up to 500. All right, so we go from D to E, but on our way from D to E, we close off the hysteresis branch CDC. CDC has a range of 300. Okay, we've actually calculated that delta epsilon that corresponds to a delta sigma of 300. That delta epsilon is 0.001525. So this point right here okay, so now we're down at D. We get up to this point right here. That point is going to be, let's call it maybe C star. Oops. C star has a stress level of 200, and it's going to have a strain value of epsilon D minus this delta epsilon that we just calculated. So we're at 0.002827, and it's actually going to increase. So in this case, I'm going to need a positive sign here. Remember, the sign that goes with this change is based on whether we have an increasing branch or a decreasing branch. Right now we have an increasing branch, so I'm going to add. So we get 0.002827. We're going to add the 0.001525 to that. And so when we go back to this plot, we're closing this branch. Oh, let me check here real quick. And the reason why I paused is because I actually made a little mistake right here. The point C should be at 004352, and I grabbed the wrong number. Okay. So I need to fix this. The calculations are fine, I just wrote down the wrong number on this plot. So when I originally wrote down point C, it should have said 0.004352. And the reason why I caught that as an error is that this point, when I take my epsilon d and add this delta epsilon, should have gotten me back to the same spot, and it does. So this is equal to 0.004352. Okay. Alright, so now we completed the branch from D to C. Because of the material memory, now since we've completed that loop, we forget about that. And here's the thing that always trips up students, is when we complete the branch from B to A, same as E again, B to E, the same as A, it's like that this branch doesn't occur, and we go back and we use this as the origin. Let's see if I can write that down. Okay, so now with point B as the origin, the change in stress goes from minus 200 to 500. Okay, so the total change in stress is 700 megapascals. The most common mistake that I see students do is that they think, well, we're already at 200, 200 to 500 is 300, so I'll just throw in a delta sigma of 300 and calculate the strain. That won't work. We need to identify where the tip of that hysteresis loop was. It was all the way down at point B. So the hysteresis branch, the delta sigma starts at point B and goes up to point E. That gives us a total range of 700 megapascals. And so I'll just make a note of it there. It would be incorrect to use delta sigma is equal to 300 megapascals. Well, we've done the calculation for 700 already. So I'll write down the result. The strain at E is going to be equal to the strain at B plus a delta epsilon from B to E. It's going to be the 0.004352 0.02143. Now we're increasing, so we use a plus sign. 0.006192232. We end up with epsilon e equal to 0.008335. Let's see where that puts us. Puts us right back where we should be, where we have rejoined the stress strain curve. Okay, so we have our strain, then our stress of 500. All right. So I would expect you to be able to do these kind of calculations either by hand or eventually with your computer program. All right, so I think that's good enough for this example, and we're in a place now that I think we're ready to talk about strain life, fatigue, and then this will just ease our way into our discussions later on variable amplitude fatigue calculations.